Alright, let's fucking do this thing. I've tried to fucking make this video like 3 times already. It's just not working. Alright, so we have some line charges, and they look something like this. Bang. And bang. This is not to scale. These are each 0.6 meters. It's meters. I was trying to figure out units. Not that it really matters. They're both 0.6 meters away. So one's obviously at negative 0.6 and one's at positive 0.6. We're trying to find a point P, the E, the electric field at some point P. So as soon as you know that you're working with line equations and you want an electric field, you should know that you have an equation available to you called the line equation. And it looks like this, my friends. Where it's just your line charge density, rho. Sometimes I've seen lambda for line charge too, by the way, but it's not really important. And it's over 2 pi epsilon naught, and then it's multiplied by your unit vector of some r. So that's our line charge equation. How is that applying to this problem? Well, let's say you call this one line A and you call this one line B, right? You're going to use this equation on both A and B. So you're going to have something like this. E equals rho 1A 2 pi epsilon naught. We'll call this RAP, which is the distance from A to this point P. We add it to rho LB 2 pi epsilon naught, and we'll call this R BP. Right? So now we know what 2 pi epsilon naught is, because epsilon's just epsilon naught, right? I already wrote that in on accident. But we don't know what these are. Well, we kind of do. I'm just going to plug them in. They're these. So we just need to find the vectors, and then our problem will be done. So the first thing we can do is simplify the problem, which is by doing this. Rho LB is equal to negative rho LA. You can see that, right? Because B is just negative 0.4 and A is 0.4. So we can do something like this. RP minus rho LA. All I did was plug in this value right here. But the nice thing about that is that we can factor. So now we have a nice problem that looks like this. Rho LA 2 pi epsilon naught multiplied by RAP over RAP minus RBP over RBP. So it becomes a really fairly simple problem. Now all we need is the RAP and RBP values, and then we're done. Because this right here, we have all the units for it, and from what I got, I'm not going to do the actual math, but looks like this is 71.9 10 to the 3. So you have that. This is just a big constant now. So now all you have to do is find your RAP, RBP values. So, and these are vectors, of course. So you should probably put those things on there. So let's find our RAP, RBP values. That would be X. So A is equal to 0.6 z. And you can see that because 0.6 on the y. Doesn't it say? Yeah, it's on the x equals 0 plane, and then it's rising all through z. So you can see that A is that, and then P, we know P to be x0z, and that comes right from, oh, whoops. Shit. That comes right from here. So RAP is P minus A, x0z minus 0, shit, 0.6z is equal to x 0.6, and this z and that z make a 0. So that's all you're left with. There's just values. You don't even have a z value. Similarly, RBP equals, all this is pretty much the same. Fine, I'll write it down. Why not? x0z minus 0, negative 0.6 z. And that will equal x negative 0.6. Okay, so now you have all those values. What do you need to do next? You just have to plug in, this color here. You just have to plug in these guys. So, equals 71.9 times 10 to the 3 times x. Now I'm going to start using the book's notation would do it like this: x ax 0.6 ay. I don't really like that notation, but I'll do it for the rest of this problem. Over and then minus so you can see right away that these y values are going to cancel. Or wait, no, these x values are going to cancel because they're negative. So you solve this, and remember, absolute value is just the, square of all that stuff. So solving this, you would get 8.63 ay over x squared plus 0.36. It's no surprise, right? Because you're it's like a quadratic, right? And kilovolts per meter. So that's your final answer. And then for part B, let's do part B now. It basically wants the same thing, but now at some point Q instead of P. So you don't even really have to start the whole problem over. You can still use this equation that we found earlier. Actually, I'll just write. I'm just going to use this value because it's the same thing. It's just, don't get confused. It's just the rho L over 2 pi epsilon naught number. And then you multiply that by R. What was the value they used here? Q. So it'd be RQP. RA Q. over RBQ. So now we just have to find RAQ and RBQ. And A is still 0.6, Z, B is equal to 0, negative 0.6, C, and then Q is equal to 2, 3, 4. Am I right on that? Yeah, 2, 3, 4. Okay. So now equals oh shit, that's one little minute detail. For this, we're going to use 4. So this will be 4. For this Z, we'll do 4, so it's going to be 0. And the reason we do that is because when we have a line, and then some point, when we're using the line charge equation, we have to kind of take it at the point that's like equal, because that's kind of how the line gets distributed through the point, I guess you could say. It's kind of hard to explain, but like, yeah, you just use that. You use this point. So if this point was like 4, you'd use 4. That's why we're using 4. So then that equals 2, 2.4, 0 equals 2, 2.4, and then RBQ equals 2, 3, 4 minus 0, negative 0.6, 4 equals 2, 3.6, 0 equals 2, 3.6. So similarly, if Q equals 9 times 10.3, 10 times 3. 2ax plus 2.4 ay over this magnitude minus 2ax plus 3.6 ay over this magnitude you kind of notice nothing really looks to cancel here, so you end up with 625.8 ax minus 241.6 ay, and volts per meters, obviously. All right, there you go. Peace.